Okay, so now if you remember the previous set of videos, we started with Newton's laws and we derived a bunch of conservation laws, right? Energy, momentum, angular momentum. I'd sort of like to do the same thing here with the Euler-Lagrange equations. But the interesting thing about doing it this way is that you really get to something much more fundamental. This is something that was first worked out by Emmy Noether. I think I'm pronouncing Noether correctly. In the early part of the 20th century, she realized that when you take this Lagrangian approach to the physics, that all of the conservation laws actually correspond to fundamental symmetries of nature. And when I say that, the first thing you might think of are sort of geometrical symmetries of shapes or something. But really what we're talking about is invariance to sort of arbitrary definitions. For example, the first example that we're going to look at is the third one in this list, energy conservation that's a consequence of time invariance. What do I mean by time invariance? It means you can basically do your experiment on whatever day you want and you'll still get the same answer, right? The physics doesn't care about the absolute definition of time. It doesn't care about where you set your origin of the time axis. And the same things are true for space and for direction in space, for translation and rotational invariance too. And we'll see how those give you conservation of linear momentum and angular momentum. Okay, so let's just go through and show how these work. Energy conservation. So this is the one for time invariance. So the way we're going to sort of encode that into the math is to say that in general, the Lagrangian can be a function of position or velocity or time, but let's assume it's not an explicit function of time. So let's assume that the partial derivative with respect to time of the Lagrangian is zero. Okay, so we can now use that by writing the total derivative of the Lagrangian with respect to time. And normally for this function of 7 scalars, 3 position, 3 velocity, and 1 time, there would be 7 terms in the full partial derivative breakdown of the total derivative. But there's only 6 here. So let's get rid of the one that has to do with the partial derivative with respect to time. Let's assume that is 0. That is our assumed time invariance. Right, doesn't matter what the value of t is. It's just the physics only depends on the positions and velocities of the particles. Okay, so you know how to write out the whole partial derivative expansion here. I guess I could have done this in a little bit more detail, just by writing, the x dot is dx dt, because just to show the chain rule, or dx dot dt for the second one. But you know what that looks like. Let's also write this in a slightly different way. We've seen this partial of the Lagrangian with respect to position before. That's just one side of the Euler-Lagrange equation. So let's just substitute in the other side of the Euler-Lagrange equation. It looks a little more complicated that way, but when you look at these two terms, you can realize that they are two components of a single derivative, right? This is a product rule type thing. This is really, these two terms are really the time derivative of the quantity x dot dotted into the partial derivative of the Lagrangian with respect to x dot. Right, when you do the derivative with respect to x dot, you get the x double dot and you leave the other one alone. When you do the time derivative of this one, you get this thing up here and you leave the x dot alone. All right, okay. So now the total derivative with respect to time is just this time derivative of this other thing. And now we just have an equation with 2 total time derivatives in it. And you can combine them together to show that the time derivative of this thing in parentheses at the bottom is equal to 0, just rearranging. So if that's true, then that means this thing in parentheses is a constant with time. The traditional thing is to call that the Hamiltonian of the system with a script h there. And if that's constant in time, we can now write out what it actually looks like. We know what the Lagrangian looks like. It's the kinetic energy minus the potential energy. And again, for a conservative system where the potential energy is only a function of position, the derivative of the Lagrangian with respect to velocity only involves the kinetic energy component. And we've written that out before. Now dotted into x, that's just going to be the momentum dotted into the velocity, which is just m velocity squared, which is just twice the kinetic energy itself. Now, if we plug that in for the first part of the Hamiltonian, then it's that thing minus the Lagrangian. So it's 2 times the kinetic energy minus the kinetic energy plus the potential, and it boils down to the kinetic plus the potential. That's the total energy of the system for a system driven by conservative forces anyway. It's just kinetic and potential. And we've shown that's a constant. So we have now shown that total energy is a conserved quantity. It's a constant in time as a consequence of our assumption way back at the beginning that the Lagrangian does not depend explicitly on time. Okay. Now we can do it. We can do it for the other conservation laws too, like linear momentum conservation. So this is the one that says, that I said on the first slide, that corresponds to translational invariance. In other words, energy invariance said it doesn't matter on which day of the week you do your experiment. Here it says it doesn't matter what room you do your experiment in, right? You can always do an absolute translation to some other location in space. Doesn't matter where you put the origin in your spatial coordinate system. Essentially this means you can put the origin wherever is the most convenient for solving your problem. Right, so again, mathematically, what this means is that if we replace the position vector x with something else, with x plus some fixed displacement delta x, then the physics ought to be the same. Now, if we just put that idea of the physics ought to be the same aside for a second, let's just see what would the consequences on the Lagrangian be if we just made this, this small displacement in x. If it's a small perturbation and you want to figure out what's the perturbation in the Lagrangian, well, the mathematical way to do that is something like a Taylor expansion. You know that the Lagrangian depends on position and depends on velocity and depends on time, but not explicitly, as we've just seen. So that means that the perturbation to the Lagrangian just is, dependent on the displacements as I'm writing them here. Now, one of these we can actually get rid of right away. I haven't even defined what delta x dot means. It's the time derivative of this delta x displacement. But if it's a fixed displacement, if it's just some constant that we've tacked on to the displacement vector, then the time derivative of it is going to be 0. So that term goes away. So the perturbation in the Lagrangian is just this first term. But now remember what we wanted to assume. Just like in the earlier problem, we assumed that the Lagrangian did not depend on time. Here, we want to assume that the Lagrangian does not depend on any spatial displacement. So that means that we really want to bake into the system that this delta L is equal to 0. We want to assume that the Lagrangian with x and the Lagrangian with x plus delta x is the same Lagrangian, same physics, no matter how you displace the system. So that means that the delta Lagrangian has to be 0. All right, now we've simplified it a lot. This one term equals 0, and we can even simplify it more. Again, going back to our thinking about waves and dispersion relations, this arbitrary displacement in space, it only makes sense to the problem if it's non-zero. So the only thing that can be 0 is, in this particular problem, is the partial derivative of the Lagrangian with respect to the spatial coordinate. It's the gradient of the Lagrangian, essentially. So in this system where we're just taking x and shifting it by a certain constant displacement, the gradient of the Lagrangian is equal to 0. All right, now this term on the left here is just the left-hand side of the Euler-Lagrange equation. So we can then assume that the right-hand side of the Euler-Lagrange equation has to be equal to 0 in this case. And now that right-hand side is a time derivative of a thing that now equals 0. So that means that thing has to be a constant. And what is that thing? It's the partial derivative of the Lagrangian with respect to the velocity. And, well, we've seen that several times now. That works out to be, for our standard definition of the kinetic energy component of the Lagrangian, that turns out to just be the momentum. So we've shown that the vector linear momentum is constant. Linear momentum is conserved, and it all comes down to assuming that we had no change in the Lagrangian by moving this system by a little displacement in space. Okay. I hope that makes sense. Yeah, kind of elegant that our choice of origin in time and our choice of origin in space, both of them have direct consequences on these conservation laws. Now, I'm not going to go through it in detail, but you could do the same thing. You could turn the same cranks by looking at rotational invariance, a delta theta rotation, and assuming that the Lagrangian doesn't change, you can eventually show that the angular momentum is a constant as a result of this not caring about which direction you're pointing. Yes, right. So this is a very general thing. This is sort of, in the last 100 years, it's sort of taken the physics world by storm as a very sort of fundamental result in classical physics. And in fact, there are other applications to it too. There are all sorts of quantum mechanics and particle physics applications of it in group theory. But yeah, however you choose to define your origin in space or time or ... I put there, the physical laws should remain the same. The ... just reminds me of another example of a choice of origin. In electrostatics, we have our electric field. Most of this course, we've worked with the vector E itself, but because the electrostatic force is a conservative force, you can write that E as the gradient of a potential. And I'm sure you've seen those potentials before, electric potentials, measured in volts. And for those potentials, it doesn't matter where you define the 0 point, right? It's all just, it's like an origin. You can choose it based on what makes the most sense, what makes your problem solving the simplest. And it turns out when you look at the Euler-Lagrange equations in this case, the arbitrariness in the choice of electric potential has a direct consequence. If you assume that the physics doesn't care about that, that tells you that electric charge is conserved. It's a conserved quantity. Anyway, interesting. Yeah, no, I think it's always good to go through this at least once in your life to see how this works. I have no idea what that lizard is in this one slide on Noether's theorem that I found online. But yeah, there's been a lot of books and conferences about it, and you can read more about it. Hopefully I'll have some more interesting aspects of it in the description below. All right.